Nanoscience wasn't correct, and so I had to fix it just now. right, hello everyone. I think only about 2 people responded to that, so I'm going to try saying that again. Hello everyone. Hi, yay, there's everyone, awesome. Hello, my name is Dr. Rita Blake. I'm the Manager of Education here at the California Nanosystems Institute at UCLA. So welcome to CNSI and welcome to UCLA. I will be your MC for today. So quickly, I just wanted to give you guys a brief overview of CNSI, since for you parents who are coming to see the presentations today, you may not be familiar. So CNSI is very different than most departments on campus. So many departments are academic. We are not strictly an academic department. We are a research institute. So we facilitate research that is collaborative and in the nanosciences for researchers who come from all the buildings that surround us. So all the different science, technology, engineering, and mathematics institutes that are around us. So we have researchers from the School of Physical Sciences, from Life Sciences, from engineering, from medicine, from math, all over. And they come to do research here that is based in nanotechnology. So we have a few different things that we do here at CNSI. One is, again, facilitating this team science. One is we house a bunch of really cool tech centers that have a lot of really nice instruments that we use to look at nanomaterials and make nanomaterials, and your students got to see a lot of those this week, so they may talk about them in their presentations. And also, we house an incubator that has around 20 or so startup companies, some of whom range in the nanosciences as well. And of course, we have an education platform where we do workshops for teachers, we do public outreach events, and we run these summer programs for your wonderful students. So there's a lot of people that make this happen, and the first person I have to introduce is the instructor for this course, and the person who is to my right, who is Professor Sarah Tolbert, who is a professor in the Department of Chemistry and Biochemistry and the Department of Material Science here at UCLA. And I'm... Why don't you finish and then I'll... Okay, I'll finish really quick. The second person I have to thank, who is not here right now because she had to run to catch a flight to the Bay Area for a wedding, is Dr. Elaine Morita, who is our program coordinator, and without her, this program cannot run straight. She is the person who really, really helps us get organized, pull things together, helps with curriculum. She is a wonderful, wonderful asset and has been extremely helpful throughout this week, so I really have to acknowledge her and thank her. And there's 2 goals for this course that we hope you'll see that we've achieved with these students. So one is to expose these students to topics in nanoscience, because a lot of them maybe have heard about the word nanoscience, they might have even known what it meant, and some maybe have some more in-depth knowledge, but it's really, really hard to know and understand nanoscience, I think, until you do experiments and you get physical hands-on experience. And also, with the homework, we wanted to both test their understanding of the experiments and the concepts behind them and what the essence of the experiment was, but also give them some experience in science communication. Because it's very, very easy to repeat back something that has been exactly told to you. It's far more difficult to try and explain science in a way that's really understandable. So that was the goal of the homework, and you will see that reflected in the final presentations. And it's been an incredibly busy week for them, as I'm sure they will tell you, because this program is only 5 days, and we have a lot to cram into 5 days. So they did 5 different experiments that you're going to be learning about today, and I am done at this point, so I think now I will hand it over to Dr. Tolbert to talk a little bit more.
Okay.
Yeah. Is that thing on? Yeah, it is on.
Yeah, it's on. Okay, so first off, I would like to start by adding a few more acknowledgments. So first off, Rita is the driving organizer of this program, and so I think it would be good to give Rita just a small round of applause for all the work that she has done. But then I also want to point out that there were 5 days of experiments, and this 5 days of experiments was run by about 25 or 30 graduate student researchers that are drawn from across the departments that are a part of CNSI. So from chemistry, physics, engineering, medicine, biology. And these graduate students are the ones who have worked hour by hour, detail by detail, with all of your students to actually make sure that they can really do these experiments. And so we have some of our graduate student mentors here, and others will come in and out as they have time. But I would just like to take a moment to acknowledge the incredible amount of work that all of these graduate mentors have done. Okay, so to get us started, so let me first start by saying I'm a professor in the Department of Chemistry and Biochemistry and in Material Science and Engineering, and my research group works on nanoscience and how we could use nanoscale materials to create exciting things like batteries that charge faster, or magnetic switches that use less energy, or windows that are clear but can be highly thermally insulating. And it turns out that nanoscience is a great way to do all of those things and many others. So what you are going to hear today is something about each of the 5 experiments that your students focused on for each of the 5 days. So the way the days were structured is in the morning they would do an experiment, and then in the afternoon they would do some other activities that were related to experiments, many of which took advantage of some of the really high-tech facilities here at UCLA, like the nanofabrication clean room, or some of the microscopes that can be used to image at the nanoscale. So what your students were charged to do was a challenging thing, which is to take the science that they did and find a way to represent the key concepts of those scientific experiments in a graphical manner that could be explained to a non-scientist. So to create a picture that could transmit the key concepts of those experiments. And before you say, high school students doing drawing homework, I must tell you that every scientific manuscript that anybody writes must always be accompanied by a table of contents graphic, which is exactly the same thing that we're talking about, a graphical representation of the key concepts of the experiment. So this is a process that we never stop doing as scientists, because as humans we are visual learners, and so as humans we can take in a huge amount more information from one graphic than from a lot of words. Okay, so what we have charged them to do is, so for their homework assignments, they all had to create these graphical representations of the key concepts of the experiments, and then they were turned in and graded, and all of you straight A students, there was great angst if anybody got less than a perfect score, but that's okay, that's real life. Everybody did great in the end. Now what we're going to do is have people explain those drawings to you. But the people who are explaining them are not the people who drew them. And so part of this is understanding what people drew, and part of this is how well did the drawer convey the concepts so that somebody else can actually explain it. Okay, so now here's the last rule. Part of presenting is getting up here and talking in front of a bunch of people and rehearsing and knowing what you're going to say and saying it well. And the other part of presenting is the unexpected part, which is being able to answer questions from the audience when you don't know what those questions are going to be about. And so, as parents, you have a job. And the job for all of you is to ask questions of the presenter. And they do not have to be deep, insightful questions. They can be, what in the world did you mean when you said X? They can be anything that you like, but it is really important that the presenters have an opportunity to say something and try to answer something that they didn't get a chance to prepare ahead of time. Okay, so I will be here for about the first third of this, and then I've got a meeting, I'm going to go, and then I'm going to come back. While I am here, I will beat on you as the audience and make you ask questions of the presenter. When I go, Rita, who is nicer than I am, will also try to beat on you as the audience and make them ask questions. But if she is too kind and lets you get away without asking questions, I would ask some of the graduate student mentors, some of whom are in my research group, and I know you're tough, to also help beat on the audience and make sure that people really do get a chance to answer questions, because that's a big part of the presenting process. And it's the thing that even as like mature scientists that everybody's the most scared of. You know you can give a talk, but what if you don't know the answer to the question? And the answer is, you can always figure out something to say. but you have to do it a few times to realize that you know more about this topic than the audience does, and it's not that hard to answer questions. So it's a really important part of the process. Okay, so with that, we have 11 presentations. So we have 33 students who are presenting in groups of 3. So we only have 5 experiments. That means if you do a little bit of quick arithmetic, you are going to see between 2 and 3 presentations on each of the experiments. But in many cases, they will discuss a different aspect of the experiment, because when you say convey the key concept of an experiment, many of these experiments have more than one key concept. But if you see a second presentation on the same experiment, then you already know something and you can ask better questions. So the second time around, you have an even better opportunity to ask questions of the students. And I also just want to say, it's going to be the last 2 for the Supercaps.
What's that?
The Supercaps is going to be the last 2?
Yeah.
So the last 2 groups actually get super extra dispensation.
They're actually
They're mixed?
Yeah,
Okay.
sorry.
There are 2 groups who did the experiment this morning and are presenting on it this afternoon. And so those groups get extra leeway because they did not have time to practice their presentation in great detail. They had to do it, learn it, digest it, turn it into a drawing, and present it today. So those are the brave souls who are going to do a very fresh experiment. Okay, so at that, I'm going to turn it over to Rita to introduce the first group.
All right, thank you. All right. So our first group is going to be Olivia, Sky, and Tara. So yeah, let's give them a round of applause.
Oh, so I forgot to say, these mics only pick up really close. Nobody wants to put they're afraid to be really close to a mic, but if you're not really close, it's as if you are nowhere near a mic. So, and if you're short, tip it down. If you're tall, tip it up. There's no way around it. You got to just do it.
And it's important to talk into the mic because, as you guys I think all know, we are live streaming. So for the people that are watching on the internet, they will not be able to hear you at all if you do not speak into the mic. Also, I will have a timer here that will let you guys know how you're doing in terms of time. So try to stick to about 5 minutes for your presentation.
We will not drag you off with a large hook if you go over, but people will eventually get really bored if everyone goes over.
Okay, so hi, my name is Olivia.
My name is Tara.
I'm Sky. And our presentation today will be on photolithography. So just as a basis, lithography means the transferring of an image from one surface to another, but specifically photolithography is using light to transfer to the image to a light responsive surface. And so, okay, basically as a summary, lithography means patterning. And just as like a tension reliever, I'm going to say a joke about light particles because I can feel like the tension here and it's really bad. So yeah. Okay. So a photon enters into a hotel room and checks in, and the clerk asks, "What can I help you with?" But the photon says, "I don't need any help. I'm carrying light." Okay. Okay. Sorry. Moving on. Okay, so you're probably going to ask, what does photolithography have to do with my life? It's actually really like applicable to every aspect of your life, whether it's biological, medical, or like your everyday applications like your phone. It's in every part of your life. And just as another basis, we're going to say the 6 steps. So the first step is coating the photoresist. Oh, wait, actually. So the first step is having the base layer, which is the substrate, and then you're going to coat the substrate with the photoresist, and then afterwards you're going to align the masking, and then the third step is exposing it to UV light, and then you develop a resist pattern after that. And then the 5th step is etching, which is removing any unnecessary particles, and the last step is stripping, which is when you clean the photoresist off.
Okay, so I'm going to be talking about our lovely drawing. So here we have, it's basically an arts and crafts project. So you can see the first rectangle there is a piece of paper, and that we believe represents the substrate or the base layer. And then as you can see, it goes on to the glue being squirted out into the design of a face. And we believe that was representing the photoresist and also the masking. And then you can see glitter is poured on to the whole paper. And we interpreted the glitter as the UV light, such as like when it's being exposed. So the glitter is the exposure, and then you can see that in the last piece of paper, it's all the glitter that was on the paper is gone. So it's just the remaining glitter is on the glue, and that represents the etching step, which is getting rid of the unnecessary particles. But as you can see, the first has too little glitter, which basically represents the underexposure of UV light. So there was not enough UV light getting to the glitter, basically. And then the second part represents a perfect sample with a perfect amount of light, and the third sample is overexposure, which is too much UV light.
So I'm going to be going over some other science concepts that we did in this lab and some suggestions maybe for additions to the photo. So basically one of the key aspects of lithography or photolithography is for technology. And another thing with that is making it smaller and smaller and smaller. So you can fit more things on a circuit chip, so you can store more information and make things smaller, I guess. However, there are some problems with this because of UV light. Because of its wavelength, as you get smaller, it gets more and more messy, I guess. So you have to start using smaller wavelengths, and you do this using smaller beams, such as lasers, and I believe they use electrons as well. And so maybe another concept that they could have shown in the image is that how UV light, as you get smaller and smaller and smaller, gets less precise and specific.
So we're digging for that. It's not supposed to make any noise. Yes, sorry. Keep going.
And then another concept, it's just another concept that we learned in the lab, was about resistance. And so I guess a basic definition of resistance is how difficult it is for electrons to move through a wire. And so the thicker the wire and the shorter it is, the easier and faster it is for electrons to go through. And then thinner and longer wires, they go slower because they encounter more resistance. But we couldn't really figure out a way for it to be incorporated well into this image. So, yeah.
Is that it? All right, thank you guys.
Okay, so I'm going to MC the first couple of questions before I have to go to this teleconference so that you get the idea of how you're all supposed to ask questions. But I just want to make 2 points first. So the first one, and I say this to all my graduate students when they're giving talks, so this is for everybody. After you are done talking, say something to the audience like, "Thank you for listening," because the audience is sitting there paralyzed, wondering if you're done, unable to decide whether to clap. So you must say something to them to say, "It's okay to clap now, guys." So it doesn't matter what version of "thank you for listening" you say, but tell them something so that you free them from their paralysis. The second thing is just something for everybody for language, which is we give 3 topics that every group is supposed to talk about. So the science, the cartoon, and then every cartoon has a limitation. And so what are the limitations of what this graphical representation is capturing? And it is impossible for any representation to capture all aspects of the science. And it is very interesting to think about what aspects are captured and what aspects are not captured. But just for all of you, and you guys did not do this, don't say, "This is where the picture is wrong," or "This is what they left out." It's not that it's wrong or bad, it's just how far can you take this, glitter glue as an analogy to photolithography, and every analogy has a limitation. So that's what you're supposed to be discussing. But be careful of the language, because it's really easy to slide into, this is what they left out. And that's not it. That's just the limits of the analogy. Okay, so now, questions for our speakers. Okay, Rita will start the questions, but then you guys will continue, because I won't let the next group go until a parent asks a question.
Okay, so forgive me if you did say this about the UV light and I just missed it, but did you guys think about a way that the UV light wavelength and shortening the wavelength might be represented with glitter as the metaphor? Because I think there is a way actually that you might be able to do that with this photo.
I can't think of it, so if you've got an idea,
Well,
yay for you.
I guess I would think, I guess I'm thinking like, in terms of like the size of the glitter, would that make a difference with patterning here?
What do you mean with the size of the
So if you've got a smile that you're trying to do, and the smile is of a certain size, and you had different sizes of glitter, how would that affect the resolution, and how does that relate to wavelength and resolution for your actual lithography when you're making things smaller and smaller?
Well, I guess if you're using different glitter sizes, you could have gone with, like with the smile, if you use really big pieces of glitter and then you try and like make a smile with it, it's not going to come out right. It's going to be kind of splodgy. Versus if you use very small pieces of glitter and then you do the same smile, it's going to come out very well and you'll be able to see it very well defined.
Yeah.
I'd agree with that.
Yeah, and that really small glitter is the stuff that like gets on your counter and never goes away. that would be X-rays, and the big chunks that are easy to sweep up, those would be like visible light. So that's the kind of thing, is you could imagine a way to add a concept. Okay, questions from the audience? You're all so hoping somebody else is going to do it. You guys, yes, thank you.
What scale are we talking about in terms of the actual application? What's the size of the circuit?
Can you ask again into the mic?
Sure. What scale are we talking about in terms of the size of the circuits that you could make with this technique?
Well, so basically, the wavelength of light itself is in 400 to 700 nanometers. So we're in nanoscience, so we're doing nanometers. Yeah.
So let me just add a couple things. So what was the size of the patterns that you guys made? Do you know? Sort of length scale.
You mean the
Like the width of the wire. You made two different wires.
Mm-hmm.
So what was the width of the wire? Order of magnitude.
I can't remember
I'm not
exactly,
sure.
but I
Yeah,
thought
we're not-
it was large enough that you could see it, but it was.
So was it, bigger or smaller than a millimeter? I can't remember what the pattern is.
It's
A little
it's a little
It's
smaller.
Yeah, so a little small, so hundreds of microns, a tiny bit smaller than a millimeter. But this is like not a clean room. So now, do you know what are the smallest structures that you could actually make in a super fancy fab, or like the smallest structures that are in your phone? That's what's limited. That's sort of the limiting size.
I'm not sure if I'm remembering this right, but I'm pretty sure you can get it into small, like nanometer size, very, very small.
Yeah,
Yeah.
just countable numbers of nanometers, like less than 10 now, I think. So yeah, that's right. Okay, excellent job, guys. Great way to start.
All right. So next team 2, Kevin, Leon, and Aryam. Yes, every group should get applause. Y'all worked very hard. Oh, sorry, I forgot to mention this earlier too, but you guys also have a laser pointer should you want it.
Thank you.
Sorry, first group.
Oh, this is Zach's laser pointer.
But I think you didn't. I think you guys probably didn't need it.
Is it?
Starting here, they might.
I think I'm pretty sure it's Zach's. I'm gonna need that later. Hello.
Hi.
Cool. All right. I'm Leon. I'm Aryam.
I'm Kevin.
And so for the past week, the past 5 days, we have been doing experiments and learning topics and concepts in the field of nanoscience. And the reason why it is actually important to learn these concepts is that nanoscience has a big part in the future of technological innovation. And yeah, it's a really big field, and it's important to learn that.
Yeah, absolutely. Everything from the computer chips in your phone to the sensors in your car is impacted by advancements in this field. So our picture is about a fun little thing called plasmonics. Now, plasmonics is a phenomenon that occurs with metals because metals have a large number of basically, like quasi-free electrons, and that's what allows this phenomenon to occur. So essentially, when a wavelength of light hits an electron cloud that surrounds a nanoparticle, it oscillates the electrons, and there's a specific frequency at which that oscillation will turn into resonance, and that frequency is dependent on the size, shape, composition, and refractive index of the surrounding materials of the nanoparticle. And that frequency is extremely important because
when the electron starts vibrating at that frequency, it will appear to be the color that is complementary to the color that's actually hitting the electron.
Yeah. And that's because if the wavelength of light that hits those electrons is the correct wavelength dictated by those factors previously mentioned, then that wavelength of light will be absorbed.
Okay, so our drawing that we were given shows a game show that aired a while back, and it is called A Hole in the Wall. And 3 contestants would stand next to a pool of water, while a wall with holes with a specific shape and size would start moving towards them. And so the contestants would have to contort themselves into the shape of that hole so that the wall would actually pass through them and not push them in the water. And so it shows these 3 different contestants. This contestant number 1, it's really hard to see, but that says height right there, and he is 7 feet tall. The other 2 contestants, contestants 2 and 3, are both 5'5", and contestants 1 and 2 are 130 pounds, while contestant 3 is 300 pounds. And as you can see later on, the wall pushes through. Contestant 2 is fine because he is exactly the right height and weight needed to be able to contort and fill the shape of the wall, while the other 2 end up getting splashed in the water. Contestant 1, who doesn't weigh a lot, makes a little splash, while contestant 2, who does weigh a lot, makes a big splash.
So the contestants in this metaphor are representative of nanoparticles, and the wall that's approaching them is the light. In order for them to appear the certain color, then they have to be the right shape and size in order to either pass through the light or transmit through the light or scatter the light.
Yeah, and so as you can see, so contestants 1 and 3 represent how contestant 1 was too tall and contestant 3 was too wide, and you can see that only contestant 2, which represents a very specific wavelength, only a specific nanoparticle, can pass through that specific wavelength. The holes are wavelengths of light, and the nanoparticle gets absorbed right there. That's what it represents. The contestant 2 actually going through the hole, while contestants 1 and 3 actually fall down. And there was another concept that was described here, and that was that contestant 1 made a little splash while contestant 3 made a big splash. And in real life, obviously, the person who would weigh more would make a bigger splash. But in the field of nanoscience, that represents scattering, which is a big splash, versus transmitting. And so certain nanoparticles transmit through wavelengths of light, while others scatter. And so the bigger person was the scattering nanoparticles, while the taller person was the transmitting nanoparticles.
All right, so for some little constructive criticisms, this was a pretty good analogy of a fun game show, and most of these concepts are very well represented. The only thing that was a little strange was that the contestants, who we believed were nanoparticles, were actually pushed by the light, which is not exactly representative of the phenomenon described by Plasmonics. In addition, in our experiment, we made these nanoparticles out of gold using a process where we put a beaker on a hot plate and we had a stirrer in there. And if we left it on the hot plate too long, the nanoparticles would clump together and form much, much larger structures. And that concept is not represented here, but it could be something that could be worked in to more completely represent this phenomenon. And that's it. Thank you.
Okay, so 2 comments. First, I just want to remind people that it's not constructive criticism. It's an analysis of the limitations of the cartoon, and they all have limitations. But that is just a slightly different language. Every analogy has limitations, and that's just built into it. And so it's analyzing just that whole idea. So try to use that language when you're talking about this. The second comment, I just have to ask the audience, does this game show really exist? Yes. This is a sad statement about television today, but okay. That aside, we will now open the floor for questions.
Hi, can I just ask what the purpose of the experiment is? Is it to identify specific materials using light, or is it to manipulate those materials somehow and transform them into other particles?
So the purpose of this experiment was really a demonstration of this phenomenon, but if you're asking what applications we could use this phenomenon for, plasmonics can be used to amplify lasers, for example. So it could be used in sort of trying to create a more powerful laser that is also extremely small, since this phenomenon is happening at the nanoscale. However, I don't think that application is widespread. It was only briefly mentioned in a lecture that we saw. And aside from that, we created gold nanospheres and gold nanostars, just different shaped nanoparticles, using methods involving the stir table, which has heat and a stir. And that was really just a demonstration of the phenomenon.
So there was, just I guess as a follow-up, so there was one application that I did mention that was really big in terms of a possible medical applications for gold nanospheres that does very specifically use the phenomenon of plasmonic resonance. Do you remember what that was, and can you explain a little bit about it?
Yes, it was a cancer treatment. I believe it's not in clinical trials yet. I'm not 100% sure. But essentially, gold nanoparticles would be injected into an area that had a tumor, and then using UV light, which is in the biological window, meaning it can pass through biological...
Near IR light, but close.
Not UV.
Near IR.
Sorry. Infrared. one of the ends of the visible light spectrum. It's close. It can pass through biological tissue without damaging it. UV will definitely damage it, but the infrared rays will pass through the biological tissue to where the tumor would be, and they would use certain biological mechanisms like antigens to make sure the gold nanoparticles target the cancer cell, and then the infrared light would heat up those nanoparticles so that it would kill the cancer cells.
Yeah. But so the big concept, 30,000-foot view, is that after these metal nanoparticles absorb light, they absorb really strongly, so they make things colored, but then they dump that energy as heat. So it's a good way to convert light to heat, which is useful for some things. Yeah. Okay, one more question. Okay, Ty.
So I just wanted to ask, you talked about in the lab, you saw that the gold nanoparticles clump together after a while when you're heating them and stuff. Is there a way that you can make those nanoparticles not clump together? I mean, I know there is because we did it in lab, but can you talk about that a little bit more?
Yeah, you can use a capping agent that will keep them separated from each other, and so they won't clump together.
Yeah, and so those are things intrinsically in this analogy you can't put together, the clumping or the capping. Those are things that just aren't a part of this analogy. I did want to make one more comment. So you said, well, light doesn't really push on the nanoparticles the way a wall does, but light actually does push on the electrons. When I talk about it, I use that technical term, slosh. It pushes the electrons back and forth. So maybe that would be another actual connection between the cartoon and the real system. Okay, let's thank these guys for another good talk. Okay, sorry. I have to go to a short teleconference. I will come back afterwards. While I am gone, parents still have to ask questions.
And thank you, instructors, for also asking questions. This is very helpful. Also, I am so sorry. I forgot to have the first two artists of the first two drawings be acknowledged for their work, because they were both very good drawings. So would the artist number one for this drawing please stand up? Very nicely done, Ariana. And then would artist number two for this drawing stand up? Sky, very nice. All right. So let us continue with that to this drawing right here. So that would be Ben, Giovanni, and Jacob.
All right, I'm Jacob.
I'm Ben.
I'm Giovanni.
All right, and so what we kind of had is the measurement at the nanoscale. And so I'm assuming a lot of parents don't really know what nano means. It's essentially really, really small. So a nanometer is 1 × 10⁻⁹ meters. And so nanoscience, we're working with 1 to 100 nanometers, which is extremely small. It's smaller than the wavelength of light. So that's just something to say. But the reason we use nanoscience is, as we mentioned before, there's a lot of medical and technical uses for it. So we already talked about the gold nanostars with cancer, and you can use that to essentially melt the tumors, which is really cool. At least that's what I thought. And then tech, you use that a lot in phones and other different things. Sorry. And then, whatever. Anyways. But another thing that's really interesting about nanoscience is that when you get to the nanoscale, a lot of materials are really different from their bulk counterparts. So things that you make on the nanoscale are normally, at least from what I've learned in the past week, they're supposed to be a lot stronger, but also a lot lighter. And so that's how we're kind of manipulating the different particles to hopefully benefit us.
Okay, so in this drawing, there's a diver, and he's entering the water, okay? And so what we thought the main concepts was diffraction, and amphiphilic molecules. So diffraction is displayed as the sun, which is our source of light. You can see a physical wave passing through the object, and it spreads out inside the water. And so diffraction is when light passes through an object that it interferes with and interacts with it, and it spreads out like this. And so amphiphilic molecules are represented as he enters the water because the water doesn't touch him, and then he pops his head out. And so amphiphilic molecules are polar, which means they have a hydrophilic head and hydrophobic tail. Hydrophilic is derived from Greek, which means water-loving, and hydrophobic is also derived from Greek, which means water-fearing. And so the hydrophobic part can be demonstrated by the water not touching him going around as he dives in, and then he pops his head out, and it's not making contact with the water because it's hydrophobic. And it also can be just demonstrated by him saying, "I need air."
Yeah, as I'm going to elaborate on what Giovanni said with amphiphilic molecules. So the amphiphilic molecules have hydrophobic tail and a hydrophilic head. And so one side is attracted to water, which is the hydrophilic head, which is caused by having a positive charge, but the other side is a negative charge, so it needs to be in the water or be out of the water. And so, this causes things to, undergo self-assembly, which is when they automatically position themselves to be in a uniform sort of pattern, I guess, if you're speaking in bulk terms. And so these amphiphilic molecules can sometimes be used as capping agents, as one of the earlier groups mentioned, can be used to coat medicine in order to go into the body and not interact with other molecules, and that can destroy cancer cells. And with the diffraction, so the light is passing through the body and it's causing the light to spread out, and this can be explained by using wavelengths of light. There are two types of interference with the wavelengths. One is called constructive interference, where the wavelengths of light match up with each other to strengthen the effects. So that's what's demonstrated by all the lines that are visible. And the parts that aren't visible for you to see is destructive interference, where the wavelengths don't match up. And so they kind of cancel each other out. Like if you have a 1 and the -1, it'll just make a 0. Yeah, that's it. Thank you.
Questions?
What experiment did you guys do to prove this application?
Okay, well, so for the amphiphilic molecules, we conducted an experiment where we had a tub of water, and what we did was we sprinkled the top with a thin, fine film of baby powder to show us the changes that occur. And so what we did was we created an olive oil. We mixed olive oil with some ethanol to dilute it, and then we poured that mixture onto the surface of the water, and the baby powder spread out so we could see how large our diffusion of the oil over the water, how large it was. And so this demonstrated that the oil was hydrophobic because it never fully mixed with the water. And what happened was it actually expanded and then contracted. And so we had to measure it when it was the largest to show the thickness of the oil molecules. And then how we measured diffraction was we had little lenses that we would shine lasers through, and it would put a pattern on the ceiling, because on the nanoscale, there was little grooves in it that would scatter the light in a specific pattern depending on the engravings on the lens.
Hello, sorry. I have two things kind of. One's a question, the other's a little bit of a correction. So you guys kept mentioning, what was it, hydrophilic heads and hydrophobic tails, right? So which one has the charge on that?
The hydrophilic side has a positive charge, I believe, if I'm not mistaken. And the hydrophobic has a negative charge.
doesn't have a charge, right?
So wait, what did you just say?
Oh, what I was going to say is I think one of them has a charge, one of them doesn't.
That's correct.
I want to say, I'll just go off of what he's saying because I'm not entirely sure which one has the charge. I'll just go with hydrophilic has the charge.
Yeah, and no, it's
and
okay. Like these things get confused so easily, especially in like our Gen Chem classes. So like it's very common. But you guys, the charge goes to the hydrophilic. Hydrophobic doesn't have a charge, right? Okay, so now for my question. I'm sorry. So you guys mentioned like constructive and destructive interference. Could you see a problem with the analogy in this case with using the sun for constructive and destructive interference?
I do see a problem with it because well, first of all, there's not really a general pattern to the light diffraction, but also with the diver, he's more of a solid object and you don't really see any sort of grading. And so there's no light that actually passes through him.
Does the sun destructively interfere with itself ever?
No, there's no constructive or destructive interference.
Yes. So that's like my main thing here. Thank you.
Any other questions? Oh, was there one more?
What's their score?
Hopefully good.
That's a great question. They will find out their score in a few weeks when summer session sends them their grades. But they're doing well so far.
How can this work to cure cancer again? Like, can you explain that?
So the nanostar treatment? Yeah. So this hasn't been put into action yet, but theoretically what you could do is, so you create nanostars using two different solutions. I think we used some sort of citrate solution, and I can't remember what the other solution was. But you use that to form the nanostars. And what you do is, I'm not entirely sure how, but they're able to direct the nanostars through the body. And the nanostars latch on to the tumor. And then when they use the infrared light on the tumor, then the nanostars heat up, essentially melting the tumor.
I'm not actually, just to add on, I'm not actually sure if people have done this treatment with nanostars. They might have. I've seen it with nanospheres and nanorods that all have the resonance with IR. I don't think that the stars would because of their size and their shape, but I mean, I don't think that they would. I haven't seen it, but there might be some other treatment that you could do with nanoparticles of that shape. So. All right, would the artist behind this drawing also please stand up so we can acknowledge their nice work? Derek, very nice. All right, thank you guys. All right, next group. So it'll be Jaewon, Zijan, and Sihwan.
Hi. First, thank you for coming here and listening to our presentation. So in this presentation, we will introduce about biotoxicity. So biotoxicity means how substance being harmful to living organisms. I mean, things like bacteria that giving disease to human being a problem for a long time. So scientists studied about how we can suppress this bacterial growth. And I mean, some people will ask, why do we have to study all this? Because we have many medicines right now. But when we related this to nanoscience, it became a different story. Because nanoparticles are so small that they barely make a bad impact to patients. So this allows doctors to cure their patients without any side effects. So scientists found the one special substance that can kill cells really effectively, which is silver. And in biotoxicity lab, we measured how different forms of silver particles kill cells effectively. So the way we did is We prepare the yeast cells and then mix those with different form of silvers, which are ions, powders, and nanoparticles. So cells also breathe like a human, and they produce CO2, which is carbon dioxide gas, when they breathe out. So if particles can kill those cells well, they will not able to breathe well, which means they will produce less gas. But if particles are not toxic, they will not able to kill cells well, and cells will produce a lot of CO2 gases. So this picture summarizes the biotoxicity experiment. On the left side, 3 people are shooting arrows, and they're shooting, each of person shooting different kinds of arrows. So the tips of arrows have a different size. The bottom one has the smallest, top one has a medium size, and middle one has a biggest size. And on the right side, someone drew the HP bar. Like they described how much damage they got. Well, it's like, I don't like that. It's so violent.
Okay, so
hold on. However, so this picture will describe how different forms of silver will give different amount of damage to yeast cells. So,
okay, so we did an experiment on how like different types of like silver particles will damage cells. So like in our experiment, we like as you said, we use silver powder, silver nanoparticles, and like silver nitrate. So like silver powder had the largest particles, but since those particles couldn't enter the cells, they weren't able to deal damage. The silver nanoparticles had medium-sized particles, and they could enter the cell and like deal a good amount of damage. Lastly, the silver nitrate had the smallest particles, but even though they could enter the cell and deal damage, they couldn't enter the cell very quickly, so they weren't able to deal that much damage. This picture is analogous to like the different forms of silver particles because like on the top the arrow had a medium tip and it was able to deal the most damage. On the second image, the arrow had a really large tip, but it wasn't able to really deal damage, kind of like how the silver powder wasn't able to like damage the cell. And like for the third arrow, it had a really small tip, kind of like the silver nitrate, and it was able to deal some damage, but the person still lived.
Okay. First of all, I will start by correcting some things that my partner said. Long before there were any scientists, ancient Romans discovered that the silver had some yes. Ancient Romans used jugs made of silver to store water and milk to prevent bacterial growth. And in later times, even in the U.S., people started putting U.S. silver coins in milk to prevent bacterial contamination. And like my partner said, size does matter. In silver particles, silver may take on different sizes, and say in both sizes, their antimicrobial effect might not have been so effective, and but as nanoparticles, their sizes are small enough to enter cells and enough to disrupt cell functions and to break down the cell wall and thus killing the bacteria. And I would say the takeaway from this lab is that as we examine the size of the silver particles, it's important to know that small sizes or sizes at a certain scale does matter. So.
Okay, so one limitation of the piece is that it doesn't portray how different sizes of silver particles enter the cell differently. In the experiment, while the small silver nitrate enter the cells through protein channels, the medium-sized particles enter the cells through endocytosis. But in this picture, all of the arrows hit the person in the same way, which basically just doesn't show like the different methods of entrance.
All right, thank you.
All right, so I'll ask the first question. So I do agree that it does look like the method of entry is the same, but I do think that there is one specific thing about the top panel with the nanoparticle that is showing something that the nanoparticle does in the actual experiment. So can you see kind of, here I'll borrow the laser pointer for a second. So I think there's something that's happening here that is kind of a clue as to how this is also really analogous to a nanoparticle. Can you think of what that is?
I think it describes the surface area, because basically the basic concept of toxicity is the more surface area particle has, they have more contact so that they can kill like more cells more effectively. So since nanoparticles are really small, compared to like same volume, they have much greater surface area. So I think Painter explained it by a number of arrows.
Right. So when the nanoparticle enters inside the cell, then what does it do?
I'm pretty sure it harms the mitochondria of the cell, which limits the cell's ability to do cellular respiration. In our experiment, we saw that like as the nanoparticles killed the cells, like the cells started producing less carbon dioxide because they were dead, so they couldn't like do cellular respiration anymore.
So what is the nanoparticle releasing when it's inside the cell that damages the mitochondria?
Well, in this case, our silver ion may lead to overproductions of certain oxygen, what is it called? Reactive oxygen species, which is also a process called liquid peroxidation, and that will lead to the basically the breakdown of the cell wall.
Right. Right. So I think that's exactly I think what's happening between this one and this one, right? So this one is I think the ion. That's a small arrow. And I think this is meant to be one arrow that, because it's lit on fire, gets split off into a bunch of small arrows, just like the small arrow of the ion down here. So I think that is one additional thing that the drawing was trying to convey, although the artist will tell us if that was their intent afterwards. Is there one other question?
Why did the artist make it violent?
Well, I guess that's partly for the artist to interpret, but I do think it's an analogy if you guys want to explain why they made it violent.
Personally, I believe this element of violence does relate to our common understanding, because it's just simple killing and slaughter. That's something we can relate to instead of just scientific jargon.
Well, I think what I might add to what you say is that they made it violent because the silver in all of these forms are damaging the cells. They're hurting the cells, right? They're killing the cells. So that is why they chose to use a similar type of analogy here.
Yeah,
So,
I would agree.
yes. All right, so let's thank our presenters. Good job. And also, will the artist of this one also please stand up? Nicely done. And I like art that makes you think, so I appreciated it. All right, so next group. So that would be Keshav, Matthew, and Nathan. Oh, whoops. That is not the next one. It is in the wrong order somehow. Sorry, guys, one sec. Sorry, guys. Oh, I think I just skipped one. Oh, yeah. Okay, sorry. Here we go. Here we go. This is the next one. So it's Jessica, Alexa, and Sophia. Sorry about that. So let's give a round of applause to our upcoming speakers. So this is the first of our two groups that are presenting on an experiment they did this morning.
Hi, I'm Sophia.
I'm Alexa.
And I'm Jessica. And our topic was supercapacitors, which our lab was on this morning. And a big problem nowadays is trying to find a balance between high energy and not having to spend tons of time charging whatever device you're using, like your cell phones or electric cars. And that's what a supercapacitor does. And to understand supercapacitors, it's important to understand batteries and capacitors. And a battery is just a device that you charge that stores a lot of energy, but it takes a long time to charge. And a capacitor is kind of the opposite in a way that it has, it charges super quickly, but it doesn't have it can't store a lot of energy. And so a supercapacitor charges quickly like a capacitor, but it stores a ton of energy similar to a battery, and it actually has a cycle life of 100 times greater than the cycle life of a battery. And we can use supercapacitors in things like cars or buses, where we can use a method of charge or discharge to provide a kind of a greener alternative to using fossil fuels and a lot of waste.
Yeah. So now I'm going to explain the analogy here. So on the left, over here, you see someone that's like eating a platter of fruit, and it takes them an hour to digest it, and then afterwards they can run 20 miles in 3 hours. So this represents a typical battery that you'd see like a AA battery or the battery in your cell phone, where it takes a long time to charge, but once it does get fully charged, it can go for a very long time. And if you go all the way to the right here, you can see that after the person drinks water, it takes their body about 15 minutes to process the water and digest it. But afterwards, they can only run for half a mile, and it takes them 5 minutes. So this represents a capacitor, because capacitors, while they charge very quickly in the 15 minutes as opposed to the 1 hour, they also don't hold that much power, so the person can't keep running for as long as the person who ate the fruit. And so in the middle, you can see that this represents a supercapacitor, in that the person drank a fruit energy drink, and it takes them the same amount of time to digest it as it does to for the water. But this time they can run a mile, which is twice as much as they did for if they drink the water, in the same amount of time, 5 minutes. So this represents a supercapacitor because both supercapacitors and capacitors charge extremely fast, and they have the same amount of charging time. But supercapacitors, since they hold more power, they can keep the person running, or in the literal case, they would keep a device running for longer.
Okay, so another concept that we learned in the lab was how area and distance can both increase the energy that the capacitor can store. So by decreasing the distance between the two plates, a capacitor is formed, and the ions made are able to travel less between the two plates. And this then increases the energy that can be stored. And the energy stored can also be increased when the area of the plates are increased, because there's more room for the electrons. And then one suggestion that we had for this drawing was that they replace the energy drink with more water, because a supercapacitor works the same as a regular capacitor. It just represents how a supercapacitor just stores more energy.
Yeah.
Thank you. Questions? Oh, all right.
So what's the main difference material-wise between a capacitor and a supercapacitor?
So supercapacitors, the most effective ones, can utilize nanomaterials. So while like a normal parallel plate capacitor you might see in like a circuit uses like two conductive metal plates, supercapacitors make use of porous nanomaterials. So what happens is that when you have lots of like nanopores in a material, you increase the surface area by a lot, so that increases like the amount of contact that the plates can get with electrons, which means that it can carry like more electrons and therefore have more energy or store more energy.
How did you decrease the distance between your plates?
Like in the analogy?
No, in the experiment.
In the experiment today, we just placed like a thin towel with citric acid on it. So because like there's only like less than a millimeter of space between like the two plates, there's not that much distance for electrons to travel, so they can like travel faster between two plates. And like the citric acid also provides like an electrolyte solution, which makes it easier for electrons to travel from like one end to the other.
All right, I'll do one last question. So you mentioned surface area as being important. What is the difference in terms of magnitude between a regular capacitor surface and supercapacitor in terms of surface area? Do you remember?
I don't remember the exact number for like how many orders of magnitude it is. I think it's several hundred or several thousand.
Yep, that's right. So it's many orders of magnitude, like at least like 2 to 3. So it's quite the difference. So just to give people extra sort of reference. Yeah. So one thing that they learned too. So I'll just add. So about 1 to 2 grams of activated carbon, which is a very high surface area form of carbon, has the surface area of about 2 football fields for a very, very small amount. So quite the difference between that and obviously a flat plate of the same amount or the same weight. All right, thank you guys. Good job. Oops, sorry. Okay. Oh, and also the team of artists that created this, if you guys would also stand up so we'll acknowledge your nice drawing as well. It's a very cool analogy. All right, so now we go on to group 6, which is Keshav, Matthew, and Nathan.
So, hello everybody. My name is Keshav Vyas. This is
Matthew Varghese.
And
Nathan Moore.
And we will be the 6th team presenting today. And so as most of the audience has seen, our homework here during the 5-day CNSI Nanoscience program was to create a visual analogy of the concepts that we had learned. And today we'll be discussing, our group was assigned an analogy based on what we did on the 4th day of the camp, which was photolithography. So, let's begin.
So photolithography is a fancy word for patterning, and it's mainly used for small circuits and semiconductors. But we'll get to that a little later. Let's just take a look at the image first. So as you can see, there's a piece of paper. There's a stencil with a design. I'm not sure if it's a cat or like a rabbit or something, but it has a design. And then there's a spray paint. And as you read the image from left to right, you notice that the paper and the stencil continually get smaller and smaller. And also, if you look at the faces on the bottom, for the bigger image, the face loves the image. But then as you keep going down, you notice that the people continually get angrier and angrier. And that's because the actual design that is stenciled onto the paper becomes grainier, so you can't see it as well.
All right, so let's start with the science.
So photolithography is made of two words, photo and lithography. Photo basically means light, and lithography is, as what was said earlier, taking one pattern from one surface and transferring it to another. And there are many types of lithography other than photolithography, such as laser lithography and electron beam lithography.
So I'm going to be talking about the 6 main steps that we were studied in regards to photolithography. So essentially what you want when you're doing photolithography is you want to be able to copy a pattern of some sort onto a material that you have. So the specific experiment that we did, we were trying to create like a small circuit board, and we were trying to etch like a pattern onto it, etch a pattern into the copper that was on this circuit board. And the way you'll do it is you'll start off with 3 basic layers. The first one will be a base, or like a little plastic plate in which you'll essentially place everything else on. That's called a substrate. And in this case, in our experiment, we use plastic. On top of that, you'll have a small layer of what you actually want to come up in the design, the actual material. So since we were building a circuit board, we used copper. And on top of that, you'll add a special coating of a chemical called photoresist. And the coating of the photoresist is generally considered like the first step in photolithography. And once you have these like 3-layer sandwich of the substrate, in this case our metal, and then the photoresist, what you want is you'll want to put a mask on it. And a mask is this usually black piece of plastic, or this black piece of plastic with the pattern that you want, and you'll place it on top of this sandwich we have. And essentially what will happen is after you expose this now like 4-layer sandwich of substrate, in our case like copper, and then photolith, and then mask to a electromagnetic wave of some kind, it'll essentially change the solubility of the photolith layer on top. And by changing the solubility, you're able to get the pattern that was originally onto that mask onto the photolith. And once you have the pattern on the photolith, your next goal would be to you develop. Taking a step back, after you mask and expose it to the electromagnetic wave, you do something called developing, which will essentially take that difference in solubility that you created by exposing it to the electromagnetic radiation and turn it into the pattern on the photolith. Following that, you do a process called etching, which would be to copy that pattern that's on that photolith onto the copper layer. So now you have a pattern top layer, pattern middle layer, and then you still have your plastic substrate. And after that, you would do something called stripping, in which you would remove the very top layer of the photolith. So in the end, you would be left with this patterned copper layer, or pattern design that you wanted, and then this plastic substrate on which you're building everything off of.
All right, so I'm going to connect that with this image. So the paper serves as the substrate. It's like the base in which we're going to etch the design. And then the stencil is like the mask. So in photolithography, the mask lets in certain parts of the UV light. The mask covers certain parts of the paper to let UV light in some places and block out UV light in other places. And so in the same way, the stencil covers certain parts of the paper, but then it also exposes certain parts so you can see that design that's in the stencil. And then the actual spray paint can is analogous to the wavelength. So if you look at how the images continually get smaller and how the image also gets grainier, the reason for this is because the wavelength, which in this case is the spray paint can, is still remaining at the same size. So when you're making products at a small level and you're trying to retain that level of quality, you can't use a bigger tool. You need to have smaller tools to retain that quality at a smaller level. And so if you look at the image, the spray paint can still remains the same size throughout the process. And so that's the reason for it becoming grainier.
So actually, since we just established the fact that we interpret the spray can as the wavelength, keeping the wavelength the same as the actual design you want gets smaller, will lower the quality. So to increase the quality on a smaller design, you'll use a higher energy, something with a shorter wavelength, such as an X-ray or maybe even an X-ray is the primary example, but I'm pretty sure you could use gamma rays or anything smaller to create a more detailed design on a smaller scale.
Yeah, so on that day, we had the privilege of going to a clean room, which lowers the chance of defects appearing on what we're doing photolithography on. And that keeps like dust from covering some parts of the mask or like the exposed parts that we don't want to be, or like the dust would.
So the dust would, and the clean, basically because we're working with things at such a small scale, it's very easy for little dust particles or very things that are anything on like the nanoscale or whatever scale you're building your, whatever scale you're going to do the imprinting on, anything can interfere with that process. So by working in a clean room, you'll be able to minimize such interference and produce more like, repeatable results and like a more, usually more clean end product.
All right, so there are, as with any analogies, limitations to this. So one of the biggest things that we thought was limited was the photoresistant. So in the photolithography process, the photoresistant is used for the patterning process. But in stenciling, you can't really use that because the mask is helping with the process of the actual design. So you can't actually have a photoresistant thing in this example. And so that would also mean that there's a missing process in the development because without a photoresistant, you can't develop it. And this also means that the very last part, the stripping process, is also missing.
So I think to wrap this up in like very short terms, this analogy for us, this analogy is a small part of photolithography in which a mask will be used to differentiate your pattern from what you want, differentiate your pattern from the material you are etching it onto, and in this case, because the wavelength / spray can is the same size, the quality will decrease. To counteract this issue, you can use a higher energy or shorter wavelength electromagnetic wave, and that'll give you a higher image quality for the size. So thank you.
So when you guys were patterning your gold or copper circuits, how did the photoresist interact with the UV light, and is that a positive or negative resist?
So the photoresistant, when the UV light hit the part that was exposed, that became soluble. And the part that was masked, while it's still soluble, it didn't wash away during the development process. So it's a positive photoresist.
All right, I have a question. So this, really like this analogy also because it speaks to a big challenge that a lot of engineers are facing in trying to make transistors that are smaller and smaller, right? That you do come up with these challenges of not being able to make perfect things because as you get too small, you have challenges like open circuits or holes or whatever it is, that imperfections that can occur. So we're hitting a limit on transistor size, right? So transistors have become smaller and smaller, but there's a limit that we're hitting. Do you guys remember the name of that phenomenon that I'm talking about?
If I'm not mistaken, I think it's Moore's law.
Mm-hmm.
And, as it held true for a few decades actually, but recently it's slowly becoming to the point where unless there's a major technological breakthrough, Moore's law could be broken. But as of now, it's still pretty strong.
Yeah, we are basically already kind of hitting the plateau. So engineers are coming up with more creative designs in terms of how they geographically, how they orient each of the transistors like within a system. But in terms of the feature size, we are actually kind of already at that limit in terms of how small things can get. Any other questions? Yes? This will be one last question.
Could you just explain the
the process of the etching. So I understood that the UV light interacts with and makes one of the layers soluble, and that's washed away. Can you just explain what happens after that to the etching on the copper?
Sure. So basically, the etching will just remove the excess copper away it'll remove the excess copper away in the same design that was originally masked on the top layer, and
And also the photoresist protects the copper that's under it, so that's why that copper wouldn't be etched away.
Yeah. Because that's usually that's like your end result that you that it could be the end result that you want or the part that you want to wash away.
All right. Good job, guys. Thank you. And let's also acknowledge the artist who did this very adorable drawing. Very nicely done. All right. Next group. Antoine, Nate, and Caleb. And while this group is coming up, if you guys all want to get up for a second, because we've all been sitting for a while, so everyone stand up. And take a nice big stretch. And then we'll go ahead and sit and we'll continue. But I just wanted to give everyone at least a moment to stand and stretch their legs. All right, go ahead.
Hello. Thank you guys for being here and thank you guys for watching. My name is Antoine and I am a rising senior at Mano Afriton High School in the Bay Area.
I'm Caleb, also from the Bay, and I'm a rising senior at Amador Valley High School.
I'm Nate, also from the Bay Area and also a rising senior.
Okay, so in our presentation today, we're going to talk about measurements at the nanoscale. There is plenty of room at the bottom. These are the words of Caltech professor Ryan Fearman in his presentation in 1959 about a study in about an invitation to enter a new field of physics. What Feynman was referencing to is the ability to move things atom by atoms. But let's first define the nanoscale. The nanoscale is when we measure things from 1 nanometer, when we use nanotechnologies or nanosciences from 1 nanometer to 100 nanometers. A nanometer is a billionth of a meter, or as Ben said, 1 times 10 to the negative 9th meter. As a reference, the width of a sheet of paper is 100,000 nanometers. So you might ask this question, why go so small? And there's a very simple answer. Because nanotechnologies have very different physical properties. For instance, they have a higher surface area than their bulk partners. They're also we can make them move thermally using thermal solutions, and this is called Brownian motion, and this is very different than also the bulk materials. And they also can interact with biological molecules because they match them in size. That means that overall nanosciences open a completely new field of interactions with cells, and with cells at a smaller scale.
So this experiment was kind of explained earlier, but to recap, it was the experiment where we took olive oil and then diluted it with ethanol and then put that in a bucket of water to see the phenomenon where it forms a monolayer. So basically, olive oil is made up of fats, which are amphiphilic, which means they have a hydrophobic head because it's repelled from water, and a hydrophilic tail because it's attracted to water. And this is due to the polarity of the water molecules and the tail. So they attract, and the head is repelled by it because it's nonpolar. And so this forms a monolayer where all tails are touching the water and all the heads are repelled from it. So basically, it's a uniform like layer where all the heads are upright and all the tails are touching the water, similar to this analogy here. So basically, demonstrated here, the people or the olive oil molecules are dropped from a plane or a dropper, and they're all in like random configurations, but when they hit the ground or the water, they automatically go into this uniform structure where they're all upright, and it basically, the soldiers saying that they've been trained to be uniform, and this is because of the charges and their interaction with water.
Okay, so to build onto that, this concept with the monolayer, which is represented by the organized line of soldiers, can also be seen in the membranes of our cells. Except in that scenario, there are two layers, and they're kind of opposite facing, with the heads on the outsides and the tails on the insides. And this double layer is kind of used to let certain molecules and nutrients into the cell and out of the cell, and that's just one of the main applications of it. Another concept that this cartoon didn't exactly touch on from this experiment is the concept of using indirect measurement to measure data at the nanoscale. So for the experiment, what we did was we first measured the volume of the olive oil ethanol solution, which was done by first measuring that of one drop and then eventually finding of the whole solution. And then we watched, as explained by the other group, as it expanded through the baking soda, we measured the radius of the circle that the olive oil puddle was creating, and we used that to calculate the area. So with these two pieces of information, with the volume of the solution and the surface area, and also with the knowledge that it would sort of form like a layer that's sort of like a cylinder, our goal was to essentially find the height of the layer, which is only one molecule of oleic acid thick. So it's extremely small. And we were able to do this through the process of indirect measurement, where once we got both of the data points of volume and area, we were simply able to plug it into the formula volume equals area times height, and we were able to find the height. And this is essential because we can't simply get a ruler and measure something that's that small. It's only a couple of nanometers, which is like a billionth of a meter. 1 nanometer is a billionth of a meter. So it's amazing that we were able to use other measurements that are much easier to measure, such as volume and area, to find the height of the layer. Thank you guys for listening.
Let's say that I know that I've now formed a monolayer on some type of a substrate. Is there any way I could visualize that monolayer or the individual molecules or nanoparticles on that surface while also measuring the surface's topography?
So yeah, absolutely. So there was this experiment. I think it was done by George Washington. I'm not exactly sure.
Benjamin Franklin.
Oh, Benjamin Franklin. I confuse them all the time. Anyways, so this experiment. So he had at the tip of his cane, he had olive oil, and he would pour it onto a lake. And what we saw is that since there was this monolayer, the surface was completely calm for the circle of the olive oil being dropped. And the rest was wavy. The rest of the lake with actual water was wavy. And that was the way to distinguish where there was the olive monolayer, because it was completely flat and the rest was wavy. That was a way to figure it out.
What if I wanted to image, say, just 2 or 3 molecules or nanoparticles on a surface? Is there any technique I could implement to do so?
Well, I assume you could use an electron microscope, because electrons have really tiny wavelengths. So when they hit the monolayer, it's the interactions that come out of that can like be imaged, and because they're hitting the monolayer is really thin, and it's only like 1 molecule thick, but the electrons are extremely tiny, so they're able to interact with it and then produce an image.
So I guess I'll add on to the question. So electron microscopes will give you a view of the surface, but it's not that good at measuring height, like topography. So it might give you sort of an idea if the surface is rough or not, but it can't really measure so much. But there was a technique that you saw, if you remember, on Monday afternoon when you went touring in the different labs. Do you remember what that was?
Was that the microscope that instead of using like light or electrons, it used the probe that's only one atom thick at the very like tip of it, so it's able to like run over it like a person like reading Braille, and so when it runs over it with that probe, it's able to feel like the bumps and therefore create like an image that's like really like fine, and you can also like code it like to sense like magnetism or charge, which could be helpful because the heads are nonpolar and the tails are.
That's true. Do you remember what, just for so everyone knows, do you remember what the technique was called? It's okay if you don't, but you said the words already. You just have to put them together. So you said scanning.
Scanning.
And the thing that's scanning
probe,
it. Yeah.
Microscope.
Yeah. Nice. Good job. Any other questions from the audience? And if not, then let's thank our speakers. Nicely done. And let's also thank our artist who did this one, if they want to stand up. Benjamin, very nice. All right, so next group is Ali, Cassandra, and Jessica.
Hi everyone, my name is Jessica.
Hi, my name is Cassandra.
And I'm Allie. Okay, so to give a brief overview, the size reduction to the nanoscale, as many of the previous groups have already explained, it could give us a range of possibilities and new properties that we can all use to contribute to new and more efficient scientific discoveries. And these properties can range from either commercial effects to optical properties or even magnetic properties. So something that we may all be familiar with is the appearance of gold. And gold, we are usually accustomed to seeing a shiny colored metal, but at the nanoscale, gold nanoparticles can be a variety of colors because of a phenomenon called plasmon resonance. And in our experiment, we focused on these unique optical properties of gold nanoparticles as a result of the interactions with light.
So this drawing focuses on oscillation and plasmon resonance, as she said. Oscillation is the synchronized movement of electron clouds, and plasmon resonance is when electrons are excited by electromagnetic waves, and the electron cloud responds by oscillating with the electromagnetic waves, so just moving up and down or side to side in sync. This drawing, so the top left area, there's no movement, there's no song playing, there's no sound, so nothing's happening. But the one to the right, there's a lot of music playing, there's loud sound, and the audience is jumping up and down. And the bottom left, there's a slow song, so they're swaying side to side. And the bottom right is showing how the type of song correlates with the lyrics and invokes a different reaction among the people. So in this case, the song is the wavelength, and the people are the nanoparticles reacting with and to the wavelengths.
So building on to what the picture already shows about oscillation, which is basically it shows actually represented the nanospheres, which had only absorbed one plasmon resonance, but there can also be more than just one. For example, when you change the shape and you bring something such as a nanostar, you can actually absorb two plasmon
resonances, because when the shape changes, there's also changes in the direction of the movement of the electrons. For example, the electrons can move either up and down, or it can also move side to side, which can also be indicated by, which can be shown it had been combined the swing and also the up and down movement of the electrons.
Okay, so to conclude, there are many real-life future possibilities of what these scientific topics can do in our current understanding of science. So with plasmonics, there is a few examples that I would like to share. Some new discoveries and innovations with chemical and biosensing with plasmonics, as well as seed-mediated growth through kinetic products. So this shows how this concept of plasmonics and oscillation, although what we are learning is at the nanoscale, there are many things that we can see in the future that we might not even realize. Thank you.
Questions?
Sorry, can I get an example for like an application to plasmonics?
So I forgot to mention this, but there's something with the capture and release of circulating tumor cells through plasmonics. So specifically in the chemical and biomed topics of science, as well as seed-mediated growth through kinetic products.
Can you explain more about the last one that you mentioned? You said seed-mediated growth through kinetic products. Do you know what that is?
It was just something I remembered from our guest speaker. Yeah.
Okay. Because I'm not sure that I recall what that was either, but you mentioned it, so it sounded interesting. So I figured I'd ask. Do you know a little bit more about this topic?
I don't know if I know a lot about it, but I think when you send a certain type of plasmonic frequency through, you guys remember like gold seeds when you're growing gold nanoparticles? It dictates the topology that follows during the reaction a lot of the times, but I don't know like all that much about it.
Interesting.
I just remember reading it.
I'd love to get a question from a parent for this one. So I'm going to do what Sarah told me to do and wait awkwardly until a parent asks a question.
All right. Can you guys give any actual examples that are in application now of plasmonics?
So as previous groups have stated, there are nanospheres and nanorods, like the thing with like tumors, and how using like infrared light, we can kind of use medicine and identify tumors for early cancer diagnosis, I believe.
So to add on to that, using such structures, they also scatter light, which means that they can also be used to make decorative items because they absorb wavelengths. And when they absorb certain wavelengths, they reflect certain wavelengths.
So I guess speaking of that, so there's one application that's an electronics application that if you've got a really fancy television, you might also be utilizing this type of technology. Can you think of what that might be? Because we can get an array of colors, right, from these nanoparticles by using different materials with different sizes, right? So what could that be an application for, you think, in electronics, if we can get all sorts of different colors?
It can be used to express certain images when put together.
Mm-hmm. So for what electronic device displays lots of images all the time? And that's its main purpose. What do you think that would be? Moving images, I'm thinking of specifically.
The television?
Yes. Awesome. So one big application for these very, very small materials that display these colors because of plasmonics is quantum dots. So quantum dots are different nanomaterials that are made of different materials with different sizes and different shapes. And because of that, they have different resonances. And so they will emit different colors. So you can utilize that to make quantum dot displays for new fancy televisions. So that's one big application that's out right now.
You probably noticed, like, if you walk into like a Best Buy or like, I don't know, Costco, like it's the new thing is they walk in and there's a quantum dot TV. And the reason for that is because the way that the plasmonics on quantum dots work is that they are able to resonate so well with one another that they achieve colors that like no other TV can get. And like they're really cheap to make and they're really easy to make all the same size and stuff like that. It's like really exciting.
So not a life-saving application, but definitely a pretty cool one. All right, good job. Thank you, guys. Thank you. Also, would the artist for this one please stand up? Ethan, very nice. Very cool analogy. I love concerts where they sing blah and blah. It's my favorite music. All right. So, next drawing will be presented by Derek, Justin, and William. Yeah, let's give a round of applause.
You say want to be here, right? Yeah, okay. Yeah, I can ask.
Hi, my name is Justin.
Hi, my name is Derek.
Hi, my name is William.
For the past week, us, along with all of our classmates, have been learning a lot about nanoscience and all of its different applications in the real world. And these applications can range from something as arbitrary as sculpting a house onto the tip of a pencil, or to something as world-defining as a cure to cancer, and everything in between that. For our presentation, we're going to be specifically talking about bio-toxicity, which is when certain materials possess a characteristic that allow it to be toxic to living organisms. Specifically, we're going to be talking about silver, which is especially important because it's toxic to prokaryotic organisms. However, it's not toxic to eukaryotic organisms, which allows it to be very toxic against bacteria. And it's very effective in treating wounds. Scientists have been aware of this property of silver for a very long time and have been using it for a very long time. However, more recently, with the rise of nanoscience, scientists have been able to rethink and reorganize their use of silver particles to make them more effective. An example of this would be, again, with fighting bacteria. Silver nanoparticles are much more effective in the process of fighting bacteria. However, there's a lot of other examples outside of just fighting bacteria, like in wounds. An example of that would be, more recently, scientists have been weaving silver nanoparticles into clothing to allow them to become bacteria resistant, which would keep them fresher for longer and allow them to not smell. And now my partner Will is going to elaborate on this scientific phenomenon.
Okay. So I actually really like this picture because they're able to incorporate a lot of concepts into what little they had. So there's like three main things that I want you to notice. There's this grass health kind of monitoring. So up here it says mostly dead grass, and mostly alive. And this wall has 3 doorways, and 2 of them are the same size, and one of them is like very large, and I'll explain that later. And these 3 objects, so there's like a long line of people, a car full of people, which is, I know it's hard to see, and this bus that has like some people trickling out of it. So this long line of people represents the ions, like the silver ions that we were using in our lab. So basically, the silver ions, they enter through the protein channels, and they disrupt the mitochondrial functions. So they are like relatively like efficient but not as efficient as this. Okay. So this is a car full of people. And, so this car full of people represents the nanoparticles because the nanoparticle, okay, so. I'm gonna take a breather. Yeah. Okay. So I think it's important to notice that the car is full of people, which is pretty, is like analogous to the fact that nanoparticles are like a group of ions, right? So,
All right. So, okay.
Yeah.
All right. So basically, carry on from Will. Basically, what you see here, these cars would represent the nanoparticles. Nanoparticles, as we know, are bigger in size than as compared to these regular individual silver ions. So that's why they are drawn in these cars in a bunch. And also, as we know, that silver nanoparticles are technically just a bunch of silver ions. So thus, it's drawn with a bigger surface area. Silver powder, though it may seem small to our eyes, we know that on a nanoscale, it is actually very, very large because though we can still see it, since we can still see it, that means that it is technically not on the nanoscale. So thus, it is depicted as a bus, just like how silver powder will kind of lounge outside of a cell and then slowly dissolve, and then thus the silver ions dissolved off the surface of the silver powder will then diffuse into the cell through protein channels, and thus the slow trickling of people into the cell. So basically, these nanoparticles are naturally attracted to the mitochondria within this eukaryotic cell because typically mitochondria are located near the perinuclear area of the cytoplasm, basically meaning that they are near the center of the cytoplasm, center of the cell, and next to the nucleus. Basically, once inside the cell, silver ions catalyze the formation of reactive oxygen species, ROS for short. ROS basically is what provokes lipid peroxidization, which is basically what prevents DNA from further developing, and thus when we did our yeast experiment, we saw that it then restricted cellular respiration, and thus no more CO2 was produced from this experiment. Along with the cellular membrane, the mitochondrial membranes are also disrupted, which completely obliterates the cell membrane, and thus mitochondria breaks down, and thus the cell is rendered useless. And thank you.
Well, so many for this one. All right.
Hi. So, can you guys clarify the following terms? Mitochondria, lipid peroxidation, and yeah, those two.
All right, so as we all know, the mitochondria is the powerhouse of the cell. All right, sorry, I just got to put that out there. Mitochondria is basically what we know is what I think is the major center for producing ATP during cellular respiration. Lipid peroxidation, yeah, is basically a chain reaction that results in polar chemical groups being attached to the nonpolar tails of these lipids in a membrane, and thus making these hydrophobic and useless, and thus this hydrophobic balance is then disrupted, and then the whole cell membrane is just destroyed.
You said that the silver nanoparticles were only destructive for prokaryotes and not eukaryotes. What are those and why is that?
Well, prokaryotic cells are basically unicellular organisms, so they only have one cell, whereas eukaryotic cells would be multicellular, and you know the reason why.
I'm actually unsure if they are harmless to eukaryotic cells. I'm not sure about that one.
Okay, so one of them has one cell, one of them has many cells, right? So if you kill the one cell, how does that disrupt the many cells?
So you mean like, for example, destroying the mitochondria in the eukaryote, or?
Yeah.
All right, so if you destroy the mitochondria in the eukaryote, then it would render the entire eukaryote as useless as well then, right?
It would lack the means to produce efficient energy for the cell because it's losing cells that could produce the energy that it needs, I would think.
Okay. So it's just like killing one, but like when it's a eukaryote, there's a lot of cells, right? So it can't kill all of those cells. Does that make sense?
Yeah.
Yeah, okay. Thank you.
Hi.
Hello.
I was going to talk about the silver powder.
Mm-hmm.
Could you please describe a couple of factors that affect the rate of diffusion of those ions?
Okay, well, thank you for giving me this opportunity to redeem myself. So basically, the silver dust, they're like these clumps of like silver atoms, right? And you can see it by the trickling is analogous to like that slow like dissociation of the silver ions from the surface of the dust particles. So that's why they're the most inefficient at like disrupting the mitochondrial functions.
So if you're comparing the surface area, because surface area is always the thing that we love talking about with nano, how would the surface area compare between the nanoparticles and the powder?
I'll take this one. All right, so basically, nanoparticles, the surface area is much larger, and thus that's why we see here on the little grass diagram, it says dead grass, because it's basically symbolizes that it does the most damage. Rather compared to silver powder, it's just a round surface, thus it doesn't cover that much surface area. So it's relatively just mostly a live grass.
So for the same volume of powder versus nanoparticles, if there's more if there's more atoms on the surface of the nanoparticles, more of them can dissociate more quickly, right?
Right.
All right. Good job. Thank you.
Thank you.
All right, and can we also acknowledge our artist for this one as well? If they would like to stand up. Are they here? This guy here? Oh, she's in the bathroom. Okay, well, let's give her a round of applause anyway. All right. All right, so next group. Group 10. So that'd be Claire, and Meghna.
Hi, my name is Claire. This is Magna, and this is Claire. We're going to be talking about supercapacitor. Supercapacitor is a combined version of capacitor and battery, so it has high energy material and high power. Solving energy storage issue enables new technology like supercapacitor. It used various transportation industry like buses, racing cars, and trams. Supercapacitor can be charged really fast and often, and it has enough power to go to the next stop and then can be recharged, so this process can be repeated several times. It is very interesting topic to improve energy storage and charging cycle. Already in China and Japan, they've been using this technology in trams and buses. Nanoscience in this topic is that nanoscale particles are very useful since it has very, very high surface area. Now we'll be explaining about the analogy and then supercapacitor in more depth.
So in this drawing, we're going to be talking about batteries and capacitors. So a brief explanation of what they are, which Claire will go more into depth about later, is battery is basically a source of energy which provides a push or voltage of energy to get a current electrical energy flowing. And a capacitor is similar, except it only provides the sufficient energy needed before it gets to the next stop, so just providing enough energy. And then supercapacitor is almost the same, except it can be charged and discharged continuously. So this drawing is supposed to be a model of an experiment we did this morning in which we tried to create a representation of a supercapacitor to try to get a red LED light to flash. So in this drawing, if you can tell, it's split into 3 parts, and each part is supposed to represent either a battery, capacitor, or supercapacitor. If you look towards the bottom over here, it shows how much energy or nutrition each dinosaur is taking in. So at the bottom, the lowest dinosaur is taking in the most energy with plus 100, but it's producing the least amount of power. So it's the slowest one, meaning that it would be the battery because it needs the most energy, or it stores the most energy, but produces the least power. The middle dinosaur, first of all, the dinosaur is significantly larger than the other 2, and supercapacitors are significantly larger in surface area compared to a capacitor and a battery. And in this one, if you can tell, it stores the second most amount of energy, but by the arrow you can tell that it's the most powerful, or it moves the fastest. And at the top over here, this is a capacitor, and you can tell because it stores the least amount of energy with just plus 10, and it's still faster than a battery, but slower than a supercapacitor.
Okay, so something this analogy doesn't really go into depth for is what's going on internally. So the reason why the battery is so slow is because actually the ions travel through it, opposed to the capacitor and the supercapacitor where the ions travel on the surface area. So basically in the battery you have the lithium ions moving from the cathode to the anode, but unfortunately this is a really slow process. So it actually can store the most amount of energy, but it is the most slowest. So that's why it's kind of like when you're charging your phone, you get frustrated because it takes so long to charge. That's what's going on in the battery. It's the process, the lithium ions taking such a long time to actually complete the process. Now with a capacitor, it's actually much faster than the battery because unlike traveling internally with the battery, the ions actually travel on the surface area. And surface area and distance is a really big part of the process. So in a capacitor, you have 2 plates, one with the negative charge and one with the positive charge. And basically, the position results in a relationship where it's very easy for these charges to pass an electric current, which makes the energy. So that's why this is a much faster process than the battery, because it can actually send an electric current at a much faster rate than the battery. Now with a supercapacitor, it contains assets from both the capacitor and the battery to ultimately reach the goal of making the most efficient product. So it is much faster than both of them because unlike the capacitor and the battery, it actually doesn't contain plates and the ions don't travel in the center. It actually, you have a porous nanomaterial, and since it's porous, it actually has a lot of surface area. So you have the the negatively charged ions on the surface area, and since it's such a large surface area, you can have a lot of ions. And you also have the negatively charged ions right next to it. So you can look at this relationship and see that they're very close to each other. So it's really easy to send an electric current back and forth, which makes it the most fastest one. But unfortunately, it can't store the most amount of energy. So that's kind of the challenge when we look at supercapacitors. We have the speed, but it's like, how do we make it store the same amount of energy as a battery can? So that's kind of what this emerging field is trying to explore that concept a little bit more, so we can eventually put this supercapacitor that functions like a battery and a capacitor at the same time into things we use in our everyday lives. So yeah, thank you.
Questions?
So a common application for supercapacitors and batteries are in electric vehicles. So in what would a supercapacitor be able to do in an electric vehicle, and what would a battery be able to do in an electric vehicle that's different from each other?
So, go
You
ahead.
go.
Okay, I'll do supercapacitor and you can do battery.
Okay.
So an example of a supercapacitor is there's a bus, I think, in Japan that what it does is, as I said earlier, supercapacitor just charges like sufficient energy from like, for example, one stop to the next. So at the first stop, the bus would charge just enough to get to the next stop in like the 20 seconds that it's waiting for passengers to load like on and off. And then at the next stop, it would charge just enough to get to the next stop and so on.
And with the battery in cars, so it has to go a farther distance than the bus, and it also doesn't have constant like charging pads, which the bus can go over. So that's why you would use a battery. But it also doesn't. So it stores more energy than a supercapacitor. So it stores more energy than the bus that Magna was talking about, but it is a lot slower process to recharge because it's a chemical reaction and not something on the surface area.
So if you remember from your lab today, when we actually pressed the switch, you guys could only see it for like a second, right? So what's different? What do you think is different about like your supercapacitors that make them like not as good as to compared to like someone who like makes really good supercapacitors?
Like what was wrong with our supercapacitor?
Well, there wasn't anything wrong with it. It worked. So like, why do you think it was not as good though?
Well, the wires we used were.
I'm talking about the actual like device you made.
Why it's not as good as like professional ones? Like, is that your question?
Yeah. So like, what do you think were like some like flaws in like the design? You guys remember that you put the carbon on each slide and you matched them up and then you sliced them together with like citric acid on top, right? So like, what's something you would do to like make it brighter or something like that?
Make it what?
Like,
Brighter.
Brighter for a longer time.
Like it couldn't have had enough, it didn't store enough energy as a supercapacitor is supposed to. It was like only storing the energy that a capacitor did, which didn't give enough like energy to go as fast as a supercapacitor should.
So like if you remember the equation, like what's something in the equation that are adjustable variables for like a good supercapacitor?
Oh, the surface area and the distance between the particles. So in the ones we made today, so yeah, surface area and distance are basically like the two main principles when you're talking about these systems, because if you have a wider surface area and a smaller distance, you can have a more faster process. So I'm guessing it has something to do with the distance and how much surface area. Well, I know that we used carbon, I think nanotube, and so it's porous, so it has a lot of surface area. So I'm pretty sure it has something to do with the distance between the charges.
All right, thank you.
I have another question. So there was a plot that Dr. Tolbert talked about when she gave you her talk, and that your instructors also talked about with reference to batteries and capacitors and supercapacitors. Do you remember what that plot was called?
I think it was, I don't know if this is the exact name, but like Rogens?
Very close, yeah.
What is it?
It's called a Ragone plot.
Okay, so
right?
it was like, so on the x-axis, I'm pretty sure it was density energy, and on the, I have it here. So the energy density, and on the y, it was the power density, and it kind of, the trend is like that.
So can you describe, so what would be where on this Ragone plot, and why? Like what is it saying?
Okay, so a battery is going to be
near the energy, and then the supercapacitor will be like kind of like in between, like in the middle of it, and then capacitor will be more towards the power.
So that means that the battery is doing what?
It has more energy in it.
Right, and
But
the
it's the
capacitor,
slowest.
but it's slow.
Yeah.
The capacitor,
has
on the other
lower
hand,
energy, but it's a much faster
faster.
process.
Right, and so
like a
it's
supercapacitor lies in the middle. It
Nice.
tries
It's
to take
like
assets from
combined.
both.
awesome. Any other questions?
When you're referring to the speed, is that the speed of charge or the speed of discharge?
So yeah, so when we're talking about speed, we mean like the amount of power that it's releasing. Especially in this analogy, if you can see, the arrows are supposed to depict how fast the dinosaurs are moving. So the amount of energy it takes in is relative to like how fast the dinosaurs can move. So we're talking about the energy it's releasing, or the power it's releasing.
But are they different? How fast it goes in and how fast it goes out? Like, can one be slow and the other fast?
Like how fast it takes to charge.
Uh-huh.
I'm not
Between
sure.
a battery and a supercapacitor?
Yeah, for any of them.
Yeah. The process for a supercapacitor is much faster because it's not a chemical reaction.
Yeah,
So you
but
don't
charge
have, like-
versus discharge.
Oh. I think it's the same.
You got it. It is the same. Which one do we usually care about?
Discharge? No.
Charge.
Well, it depends what you're doing. Where would you care about charge?
When you're like charging like your device or something like that, and you want it to go quickly.
Where would you care about
maybe, like,
discharge?
a
When you're
car,
releasing the energy?
When like how much energy you can release. Like for the buses, like the discharge is really important because it has to match the amount of distance it has to go in order to go to the next like charging pad.
No, but the speed. You were right. Buses is a big one. Why would you care about how fast it can discharge? What would that relate to in a bus?
Oh, the people getting.
Or car?
The speed?
The acceleration, actually. How fast you can accelerate. Because it takes a lot of power to accelerate. So if you don't discharge fast, then you would have a very little old lady kind of bus that would not speed up very fast. So that there are certainly places where you care about the speed of discharge, and certainly cases where you care about the speed of charge. But luckily, they're pretty much the same, so you can get whichever one you want.
Yeah, good. Yeah, nice job. Thank you, guys.
Thank you.
Okay, official apologies. I called Rigoni an old dead dude. I was wrong.
Yeah, I wasn't sure either. Oh, yes. And can we also acknowledge our other team of artists for making this supercapacitor photo in basically an hour? They want to stand up. Nicely done. All right, last but not least, we have our final group. So this will be Vivi, Ariana, and Fen.
Hi, good afternoon. I'm Vivi.
I'm Ariana.
I'm Fet. So today we're gonna lead you guys through the concept of photolithography. And I know a lot of groups has already mentioned it before, but very basically, photolithography or lithography is just the process of patterning something to another thing that you want to have the certain pattern. And photolithography is the patterning process, but with the help with light and all its different wavelengths. So for example, there are visible lights like the white lights that's shining on my face, the red lights, green lights, blue lights, all those kind of stuff. And there are also UV lights that comes from the sun and X-rays and all of that. So I want you guys to do an exercise because I know we've been sitting here for 2 hours. So raise your hand if you do not have a phone. I'm sorry. I'm sorry for you. Okay. Now, second question. Raise your hand if you have a phone right by you right now. Almost everyone. So why do I mention this? It's because in each phone, okay, here's a number. I'm not sure about the number because I Googled it, so don't quote me on the number. But in each phone, there are in average about 4 to 7 billions of transistors on them, which are more or less all made of or all made from the lithography process. So with such a wide usage, and here we're gonna explain the lithography process and specifically the photolithography process by analyzing this beautiful cartoon over here.
Oh, okay. So if you can't really tell from this picture, it's basically a cave right here. And then that's sunlight that's directing inside the cave. And then on the two sides, you can see that there's tunnels where there's miners coming in to mine. And then this is basically a representation of photolithography because if you can tell or not, the bottom right here, the bottom of the cave, it's actually the photoresist, which is a really light sensitive material that covers a surface. And then one of the key components of photolithography is, I believe, exposure of UV lights. And then there's actually two resulting outcomes that's possible. One of them is called a positive resist, which is when the UV light that's shown on the area that's exposed by the UV light is actually hardened. So basically, when it's washed by a solution later, that's the area that's going to remain. So that's called the positive resist. And then the other one is called a negative resist, where when the sunlight exposes on the area, it actually weakens the bonds. So the area around it is actually the ones that's going to remain when the solution washes it. So if you read the dialogue of one of the miners on the bottom, it says that we should only mine in areas with no sunlight. So that means that it's usually easier since the dirt or the ground is a lot softer. So the platform right here where the sunlight is exposed, that's a lot harder. So then this is actually a scenario of a positive resist. And then next are the tunnels on both sides. So the tunnels is actually a representation of the circuit, the wires that was printed onto the circuit board. So the one on the left is actually the thin wire, because as you can tell, the people or the electrons are trying to get through, but the tunnel is so small that it's kind of hard for them to go past. So it's a thin wire, so it creates more power and more resistance. And then the one on the right, as you can tell, there's only like 3 people standing in front of it, so it's really easy to go in and out because it's the thicker wire. And then, it allows for, it's just less power and then less resistance.
Yeah, so now I believe that this picture has really conveyed the idea of the resistance and the step of exposure very clearly, so I guess that you can all believe it. And so I'll just go through the whole process of the photolithography again so that you guys can have a better idea on this. So now we have a material, and the first step is coating. So what is coating? It's just we coat the photoresist onto the substance we want our pattern to on, and this is just simply literally the process of coating. And the second step is about masking, and it's literally put a mask on the photoresist with the pattern you want. And then it's the exposure. So you bring the stuff under the sunlight and expose it, and on the surface, some chemical reactions will just appear. And then you put the stuff into a developing solution, and this is simply called developing. And so according to the type of the photoresist, you can have either a negative photoresist or a positive photoresist. So if it is a positive photoresist, the area exposed to the sunlight will be more soluble in the developer solution. And if it is the negative photoresist, the area that is not exposed to the sunlight will be more soluble in the developer solution. And then the next step is about the etching. So in this progress, you just use a chemical to remove the unprotected areas, and the next step is called striping. So in this progress, you just get rid of the unexposed photoresist so that you can get the product you want. And this process, the whole process of photolithography contains 6 steps and is a little bit complicated. And so in order to meet the need, you can just build some more layers,
And normally, the product we nowadays use is about 15 layers. Yeah, and yeah, that's how I explain this. Yeah, thank you.
Questions?
So you mentioned that in this scenario here, if we're treating the cave as our resist, that this would be a positive resist. Why did you say that?
We said it because you can see in the dialogue on the bottom, maybe you can read it, but it says like something like if we go to the middle where there's light shining, we're gonna get burned. So in a positive, when the chemical is like positive, the area where the light is exposed becomes soluble. So whenever like the particles inside the area where light is exposed, it gets soluble, and so it like washes away, and that's why we think it's positive rather than negative.
Of the 6 steps in lithography you've mentioned, what do the minors represent here?
This represents the process of exposure.
They would be developing the resist, right, after exposure, because the sunlight is your light source here, correct?
Yes.
Yeah, I think, well, so I think that's not what they would be. So if you had to pick something else, what else could they be?
You mean other than developers, or?
I wouldn't even say they're developers.
You wouldn't say if we treat the cave as a resist?
Well, I guess it depends what you treat the cave as.
Because I would think of this as a negative resist.
So, yes. Okay, so I was hesitant to say anything because I can never keep track of positive or negative. And so I never use those words when I talk about things. I just describe the concepts because then you can never say the wrong word. I definitely recommend this to people when it's something like positive and negative that doesn't really have any deep meaning. I do a lot of electrochemistry. You can be the wrong sign all the time. Okay, so, but I think that this would actually be a negative resist. So can you guys take a crack at explaining this, assuming it was a negative resist? And so you may have to reassign what some things are.
At first, when we saw like there's light coming, we thought it was like an exposure.
Yep, that's good.
But we're just confused on why the person at the bottom would say like if we get in the middle, it will get burned.
Okay, but
we assume that it's like saying that if they get there, they become like soluble and they're like disappear. That's why they're positive.
Oh, okay, so don't take it to mean that. I think I see now. So let me give you some ways to think about it. Mm-hmm. Okay, so what did you say the light does to the ground?
It hardens it.
Hardens it. So what would that be analogous to in a positive or a negative resist?
So if it is harder, then it will be insoluble to the developer solution.
Right. So then the sun-hardened dirt would be the cross-linked photoresist. So now, what are the minors? And they could be 2 things. What do minors do in general? Just in the most vague sense. You've got a miner. They've got a shovel. What is their general job?
Mining and getting rid of the extra stuff or particles on the floor.
Getting rid of stuff. So, given that they get rid of stuff, what are the 2 things that they could possibly do in this situation?
The etching solution.
They could be the etchant, or they could be, as we said before, the developer. So the developer gets rid of the extra resist, and the etchant gets rid of the extra stuff. And so they could probably be either, depending on how deep down in the dirt, I guess you'd probably call the top layer of dirt the resist and the lower layer of dirt the stuff. Any parent question? It's your last chance. What parent hasn't asked a question?
So many of them. Not apparent, but I'll take it.
All right. Hi. Really good explanation on photolithography. So I guess I just had a question. So you guys mentioned photolithography is often used in integrated circuits to make transistors, as in your phones. So quick question for you guys. Whenever I walk by the clean room, I notice that they use yellow light as opposed to white light like we have here. Why would you think that is?
I'm not 100% sure, but yellow light, it's when you take the particle out of the machines directly, there's still like particles around it that can be really interrupting. So the yellow light is kind of more similar to it, so it doesn't immediately bring it to the white light to distract it as much.
Let me add just a leading question, which is, when light looks yellow, what colors is it missing?
Violet.
That's right. Violet is what it's missing. Why would you want to be missing the violet?
I think it's because violet has a relatively small wavelength. Yeah, that's why it has like smaller energy, and it can like less interrupt what is like the product being produced in the clean room. And that's why we use.
It has a small
yellow
wavelength,
light.
but is its energy high?
Oh, sorry.
High or low?
Smaller wavelength, higher energy.
High energy.
Yes.
And so what is it similar to? What's right past violet?
It's what you use as a hint. UV.
Ultraviolet, UV. And so why would you want to get rid of the violet? When you have your photoresist that's been partly exposed, but not yet developed.
Think about what we talked about in our first talk today.
You want to get rid of the violet. You have this photoresist, you exposed it to UV light, and then you haven't done any of the next steps. So you haven't gotten rid of the unreacted material. To be very careful, everybody looks totally dorky because you have yellow light.
So to help you out, so why, if you still have undeveloped material, would you want to stay away from violet light, which we just said was close to ultraviolet? What might happen?
I guess the exposure process would keep going.
You've got it. Yep.
Nice. Nicely done.
I have one more random question for all groups that have done the photolithography experiment, or anybody else actually in the whole class. Why is it called lithography? And what does the litho part of lithography actually come from? Just anybody can yell it out.
Two root words, photo meaning light.
Yeah, forget the photo. No, people in the class, forget the photo part. Just why is it called lithography? What does the litho part mean?
Doesn't it mean to write?
No. What is litho? Anybody? Lithosphere. It's a Greek beginning.
Can a parent guess too?
Yeah, a parent can guess. Stone. It's called stone writing. Why in the hell is this high-tech process called stone writing? Any idea how lithography started? But it's about pattern transfer.
Like sculpting and pottery and that kind of thing was the first big example of it.
Not quite, close.
Do they stamp things on stone?
They etched patterns in stone and put ink on stone and then stamped things with stone. So it's called lithography because the original pattern transfer was you etched a pattern in rock, and then you inked the rock, and then you pushed the rock down on something you wanted to transfer. And because what they ended up doing was pattern transfer, they named it after the rock they chipped at, and now our high-tech photolithography process is named after a rock, even though there are no rocks in our process. But they still retain that thing. I have done photolithography. If you walk through the airport in Tokyo, there are some people and little stations teaching you traditional Japanese art, and they will let you do photolithography between two terminals if you have time to kill at the airport in Tokyo. I recommend you stop if you're not going to miss your plane. It was quite fun.
So that makes us an incredibly apt analogy. So will our artists for this one stand up and we can acknowledge their very apt analogy?
And artists, did you know that this was really about rocks? You don't have to tell us. Don't answer.
Just say that you knew and just be like extra cool. No one will know that if you didn't know. All right, so let's all take a moment to thank all of our speakers because they all did an amazing job with all of these drawings. Good job, everyone. I hope you were all impressed by the amount of knowledge you were able to acquire in a very, very short period of time, 5 days. And good job with being able to present things with very short amounts of time to prepare. It's always exceedingly impressive what you guys are able to come up with. Sarah, did you have anything you wanted to add?
I just want to thank all the students for taking a week of your summer and using it to learn about nanoscience, because I think that the world should know about all the cool technology that is out there and know it in a real way so that you actually understand the real science behind it, because there's a lot of hype and some of the reality is every bit as good as the hype and more, and some of the hype is wrong, and the only way to distinguish is to actually go and understand the science. So thanks to all the students for taking a week out of your summer to gain that knowledge. And thanks to all the parents for sharing your kids with us for a week.
Yay. And thank you, instructors, and double thank you to instructors who were here and asking questions, because that's super awesome, and it's cool to have you guys here too. So thank you. All right, so we have a lovely reception outside with food and drinks, but before we all go enjoy those, I want to ask that all of the students and instructors who are here gather outside under the sign that says California Nanosystems Institute, and we'd love to take a group photo of everyone that we will send to you all after this program is over.
Okay, so the sign, you walk out the front door, it is attached to the wall directly to your left. So it's like 5 steps from the front door.
And please organize yourselves by the tallest in the back and the shortest in the front.